Hello and welcome to a new video. So today we're going to continue from where we left off last time. So when we talk about the majority vote system, if you remember, you redundant one bit with three physical bits like this. And so you could correct the errors using the majority vote. Okay. So if you remember, this was implemented using several XOR gates. So today we're going to see more about the mathematical aspect of this. So as it's written here, let's find out when the majority vote system for 3-bit code words works better, okay? Okay, so let's use this key here. So the green squares represent non-flipped bits, while the red ones represent flipped bits, okay? So when you have no redundancy, it means you just have one bit, one physical bit for each logical bit. So the probability of a bit flip is just p, okay? However, when you have a 3-bit string like these ones here, we know that when 2/3 of the bits are flipped, at least 2/3 of the bits are flipped, we get an uncorrectable error. So you have the case where 2 of 3 are flipped or all 3 are flipped. Okay, and you can express this this notion like this. So, for example, in this case here, we have the first one which is flipped, the second one which is not flipped, and the third one which is flipped. So if you express them as probabilities, still using p, you have p and 1 minus p because it's the complement, and finally still p. Okay. So this there you have the product of these three probabilities because of the chain rule. Okay. Okay. So you can think of 1 minus p of like this. So you have one which is 100% probability minus p. Okay. However, this is not the only combination because you can have the first and the second bit flipped or the last two flipped. So if you express them still using p, you have this case here, pp 1 minus p and 1 minus p times p times p, okay? And of course, you also have the case where all bits are flipped, which is p times p times p, okay? And so to get the overall probability of an uncorrectable error, you just need to sum all these different probabilities here, the blue one, the orange one, the green one, and the gray one. And if you do the algebra, you get 3p squared minus 2p cubed, okay? Okay, so our task now is to answer this question, which is being rewarded into two different ways. So in terms of avoiding uncorrectable errors, when is the 3-bit redundancy more resilient than plain bits? Or you can also say it as, in terms of avoiding uncorrectable errors, when is it that 3-bit redundancy is more useful than no redundancy at all? And so what you do is that you use this equation here and you compare it with p, okay? So you're saying when is the 3-bit redundancy uncorrectable error probability less than the uncorrectable error probability of no redundancy at all, okay? So this is an inequality which you can solve by hand or by using the computer. And if you solve it, you get p less than 0.5, which means that as long as the probability of a single bit flip is less than 50%, the 3-bit system will be more resilient and no redundancy at all, okay? However, if p is greater than 0.5 or 50%, our 3-bit system will be worse. And in the next chapter here, when we'll see the 3 versus the 5-bit code words, we are also going to solve a similar equation by hand and also using the computer. So here we skip this here, but we're going to do it in the next video, okay? Okay, so if you want a more formal description to see all the cases for the 3-bit strings, you can formalize them into tables. This is quite self-explanatory because you have the no error case, you have the single bit error case, which yields these results. Of course, these two tables are for the correctable error cases. So here, of course, when everything is okay, there is nothing to correct. And when you have a single bit flipped, you can correct it, okay? Then, as we saw before, we have the case where all 3 bits are flipped. which you can express it with in these three ways. So p times p, or p cube, or also p cubed times 1 minus p to the power of 0. So take note of the way this is expressed here, because we're going to use it in the next video, okay? This is going to be useful for generalization. Then we have the 2-bit flipped cases, which are these here, okay? And so of course this means we have to consider p squared times 1 minus p 3 times. If you see here, we still have the power, okay, explicitly, like we did here. You solve it, okay, you get the same result, of course, we got here, okay? So take note how this has been expressed, because as I said, we're going to use it in the next chapter. But now we're going to see an exercise. This is going to be interesting because we have some code to write as well. Okay, so we still have the 3-bit repetition code. So if p equals 0.3, where p of course is the probability of a single bit flip, compute the probability of an uncorrectable error in a 3-bit code word. And now you need to compare this result to the non-redundant single bit code word and find out which system is more resilient for p equals 0.3. So in other words, does a 3-bit system make uncorrectable errors more probable than no ECC at all? And you can answer these same questions for p equals 0.8. Then in the next point, you can write a Python script that computes the p-values from 0 to 1. Maybe you can do like a step of 0.1, so you can have 10 values at the end, for example. Okay, so you can pause the video here, and now we're going to see the solution. Okay, so of course, if we use the equation, what you need to do is to just replace p with the two values 0.3 and 0.8. So this is very straightforward, and we are going to use the Python script directly. So you can use this one here. So what it does is to generate the 10 values from 0.0 to 1.0, okay? And then what we do is to replace the 10 values each time in the equation, which is this one here. And finally, we're going to print the values in a markdown table. If you see here, this is the table header, because we're using this object here, okay? So our table will have the values of p, the uncorrectable error probability for the no redundancy case and for the 3-bit case, the winner between the two, okay? So we just compare the values from the equation with p, okay? So these are the value from the equation, 3-bit code word, okay? There's a variable here, which then is placed here and extracted as c, okay? And then we are going to highlight both cases of the text problem, so 0.3 and 0.8. And we use the bold instruction for markdown. So we have the 10 values, and we have the values for the 3-bit string after the equation has been computed. These are these values here. And then we have the table. So this table is automatically generated, okay? Okay, so if you see, of course, when the probability is 0 and when the probability is 1, it doesn't matter which system you're going to use, because you either have all bits which get flipped or no bits, okay? Then the two cases of the problem, so the first one was 0.3. If you see, when you compute it for the 3-bit case, you get 0.216, and so it's going to say that, of course, the 3-bit system is going to be better than no redundancy at all. And conversely, you have the case where p equals 0.8. The execution tells us that the no redundancy is better than using the 3-bit, okay, redundancy. Now, since this is a dynamically generated table, we can change the total values here, okay, as it's written here. We can use 20 instead of just 10. So now we're going to do that. Okay, if you see here, this is the code, which is executed each time there is a change in the quarto markdown file. So now we put 20. This is going to reload, if you see, automatically. Okay, so now we have 20 values. You see here, now it's the same. This gives you a better idea of the break-even point, which is 0.5. So this is all for this video. Thanks for watching, and see you in for the next chapter. This one here. 3 versus 5 versus n-bit code words. Okay. Thanks for watching, and bye bye.